In this lecture video, we look at several measures that are used to assess the fit of a structural equation model. In many research situations and for many theories, research questions involve investigating constraints between and among various model parameters. The research goal is to identify when constraints appear to hold and to translate such results into the language and context of the theory. Because of the way hypotheses are formulated and tested in structural equation modeling, where constraints make up the null hypothesis, from a statistical standpoint, concluding that constraints hold means that concluding that the null hypothesis is true. You will recall that failing to reject the null hypothesis opens up the possibility of a type 2 error, whereas the probability of a type 1 error, which is the significance level of the test, is under the control of the researcher and therefore known. The probability of a type 2 error is in general not known. Hence, when we fail to reject the null hypothesis, we really don't have much information at all regarding the reliability of such a conclusion. This is where assessing the fit of the model becomes important. If the null hypothesis is not rejected and the model fits the data well, this may lend credence to the conclusion that a type 2 error has not occurred and that the correct decision regarding accepting the null hypothesis has been made. Here's an outline of what we'll be looking at in this video. We'll first look at a number of overall fit statistics. The first will be the model chi-square statistic. We'll then look at the goodness of fit statistic. There is an adjusted goodness of fit index as well that takes into account the number of parameters in the model. We'll then look at what's called the root mean squared error of approximation. Next, we'll look at the comparative fit index. And for our final overall fit statistic, we'll look at the Akaike information criterion, or the AIC. We'll then look at residual analysis in the context of SEM to see if we can identify places in the covariance matrix that are not well fit by the model. So let's jump in. So let's first look at the model chi-square statistic. If the model is correct, then in large samples, the sampling distribution of the model chi-square statistic will be approximately chi-square with degrees of freedom equal to the model degrees of freedom. The model fit is considered questionable if the chi-square statistic is a lot larger than the model degrees of freedom, or if the p-value associated with the model chi-square test is really small. Now typically, if one of these occurs, the other will occur as well. Next, let's look at the goodness of fit statistic, or GFI. The GFI, the goodness of fit index, is a model fit index that measures the proportion of variance and covariance in the covariance matrix of the manifest variables that is accounted for by the structural equation model. The GFI is similar in interpretation to the R squared in regression, which you'll recall is the coefficient of determination. And in the context of regression, the coefficient of determination, R squared, gives us the proportion of the variability in the response that is accounted for by the model. And so the goodness of fit index is a similar type of index. It has a similar kind of interpretation in the context of SEM, where we are modeling not a response variable as we are in the case of regression, but we're modeling the contents of the estimated covariance matrix. Now, the goodness of fit index, like the R squared in regression, ranges from 0 to 1, with better fitting models having a GFI closer to 1. Now, according to Rakoff in his book, A First Course in Structural Equation Modeling, on page 38, models with a GFI in the mid 0.9s or above may well represent a reasonably good approximation of the data. Next, let's look at the Adjusted Goodness of Fit Index, or the AGFI. The Adjusted Goodness of Fit Index is a model fit index that is based on the GFI that takes into account the number of parameters in the model, similar to the way that the adjusted coefficient of determination, the adjusted R-squared, takes into account the number of variables in a regression model. Now, the guidelines for evaluating the Adjusted Goodness of Fit Index and determining whether or not a model provides a reasonably good fit to the data are the same as the guidelines for the Goodness of Fit Index itself. Next, let's look at the root mean squared error of approximation, RMSEA. The root mean squared error of approximation is a model fit index that takes into account the complexity of the model through its degrees of freedom. Now again, according to Rakoff, models with an RMSEA less than 0.05 may provide a, quote, reasonable approximation to the data, end quote. Next, let's look at the Comparative Fit Index, or the CFI. Now, models with a Comparative Fit Index in the mid 0.9s or above are considered to provide a reasonable approximation to the data, and this is again from Rakoff's book. Now, we're really not going to worry how to calculate these things. The SEM software is going to provide these for us. What we need to focus on is how to interpret these various goodness of fit measures and to know how to use them to determine whether or not the model provides a reasonably good fit to the data. Next, let's look at the AIC, the Akaike information criterion. Now, I'm sure that you've seen the AIC in other courses, such as a regression course or other statistical methods course. And as you'll recall, the way that we use the AIC is we use it in comparing two models. And so when used for that purpose, the model with a smaller value of the AIC is typically considered to be preferable. So this is based on the value of the log likelihood of a model in the context of, for example, regression or analysis of variance, where we're using maximum likelihood estimation to estimate the parameters in the model. It's based on the value of the log likelihood, but it takes into account the number of variables in the model. Okay, so let's look at a quick summary of these various overall measures of fit that we've looked at. And so here we have a table containing the 6 overall measures of fit, the model chi-square statistic, and a good fit is indicated when the chi-square statistic is not much larger than the model degrees of freedom, and when the p-value is not terribly small. When using the Goodness of Fit Index, the GFI, what we're looking for is a value of the GFI at or above the mid 0.9s. Similarly, the Adjusted Goodness of Fit Index, which takes into account the number of parameters in the model, we're looking for a value of that measure that is at least is at or above the mid 0.9s. When using the root mean squared error of approximation, we're looking for a value of that measure that is less than 0.05 to indicate a good fit of the model to data, which is, again, the covariance matrix, the estimated covariance matrix for the manifest variables. When using the Comparative Fit Index, what we're looking for is a value of that index at or above the mid 0.9s. And then finally, if we happen to be using the AIC, the Akaike information criterion, to compare two models, then the model that has the smaller AIC is typically considered to be preferable. Now, the thing is, we don't need to pick just one of these overall measures of fit to use when we're assessing the fit of an SEM. In fact, in many situations, we may use all of these to try to get as much information, as much insight as we can about the fit of the model. And so we might be looking at all of these and seeing if any of these fail to indicate a reasonably good fit to the data. And if that occurs, then we may decide that the model needs to be adjusted. We need to relax some constraints or something like that in order to get a better fitting model. Next, let's look at residual analysis in the context of structural equation modeling. The model fit indices described above are overall measures of fit that may not be able to detect situations where the quality of the fit is not uniform. A given SEM may fit some parts of a covariance matrix very well, while fitting other areas very poorly. It's possible in such situations for the overall fit indices to indicate an acceptable fit, even when the quality of the fit is non-uniform. Residual analysis can be used to detect such situations and to identify specific areas in a covariance matrix where a model does a poor job of reproducing the observed covariances. Standardized residuals allow for comparisons across variables and the identification of areas of poor fit. So that's going to be important to calculate the standardized residuals because it allows us to compare the sizes of the residuals across the various variance components as well as the covariance entries. A standardized residual greater than 3 in absolute value indicates an area of poor model fit. So we'll be using all of these fit indices when we assess the quality of the fit of a structural equation model. So that's what I wanted to show you in this video. I'll see you in the next lecture video.